An intelligent Iqrf gateway, presented by Martin Spiller from MICRORISC company. Few words about myself. I have been working in MICRORISC for 12 years, currently in the position of Field Application Engineer Leader. In addition to regular technical support of MICRORISC customers, I am responsible for hardware development and especially for development of Iqrf gateways. I have been involved in many projects related to Iqrf technology. I am currently leading a project to develop an autonomous off-grid system for bidirectional communication with wireless nodes. What is the agenda for this presentation? I will start with a short introduction to Iqrf technology. Then the basic architecture of the Iqrf gateway will be presented. I will then move on to the software that implements its functionality, which is called the Iqrf Gateway Daemon. I will explain its basic components, which are the application interface and the web interface. I will explain the basic difference in using Arbian and Yocto Linux. I will spend a few words on the idea of Iqrf licensing. And what are the next plans for expansion of Iqrf Gateway Daemon? Then we move on to the Iqrf gateway design. We start with the basic shield. Then continue with the extended shield and then the industrial gateway shield. Finally, I will describe the design of Iqrf off-grid gateway. In the last topic, we will discuss the Iqrf cloud. Iqrf is a wireless technology designed for communication in ISM band. It can be configured to use a specific frequency band according to local radio regulation authority. For example, for Europe it is 868 MHz, for US it is 916 MHz. Iqrf requires no infrastructure by external providers, no license and no carrier fees. It is low-power wireless technology, especially suitable for battery-operated devices. Therefore, the communication range is in hundreds of meters in free space and tens of meters inside buildings, and it can be extended further with the help of Iqmesh topology. The core device is a small transceiver module, as presented in the picture. The basis of mesh communication is the Iqmesh protocol, which is implemented inside every transceiver module. It is based on direct flooding. Each unit in the network plays the role of a repeater and forwards data to its neighbors. This significantly extends the communication range and increases the reliability of communication, enabling the technology to be used in demanding environments. The communication is synchronous. The data forwarding happens in precise time windows, so the network is strictly deterministic. The advantage of this approach is robustness and reliability, which will prove to be a major parameter in industrial applications. The Iqmesh protocol is suitable for reliable bidirectional transmission of limited amount of data. Thus, it is suitable for telemetry or control applications. In Iqrf network, there can be up to 239 devices, which can act as a sensor or actuator. At the same time, these devices can route individual packets. In an Iqrf network, there is always one device, the coordinator, which initiates the communication. Thus, to read the value of a sensor, it is necessary to send a request and read a response. The coordinator is also responsible for network construction, node bonding, and topology discovery. It is logical to place the Iqrf coordinator in a device, a gateway, which makes its functions and network data available to superior system. The design of the Iqrf gateway is furthermore the main focus of this presentation. Now, what does the Iqrf gateway consist of? The basis is a small Linux machine, most often based on the Raspberry Pi or similar devices. Then a small PCB, sometimes called a shield, is needed to connect the Iqrf transceiver to the Linux machine. The shield is connected to the I/O header of the Linux machine. UART or SPI is used for communication and several I/Os for control signals. Finally, to make the gateway operable, the Iqrf Gateway Daemon and Iqrf web application needs to be installed on the Linux machine. Both are open source software available on GitLab, where it can be downloaded and used for free. There are already several commercial solutions on the market now, which are ready to use. These solutions are based on the same architecture, and they are using the Iqrf Gateway Daemon and Iqrf web application as well. The functionality of the Iqrf Gateway is therefore defined by its underlying software layer, the Iqrf Gateway Daemon. So what is it exactly? First, it is the communication channel through which the gateway can be communicated with. The primary channel is MQTT. It is the one through which the gateway's application interface is accessed and through which the gateway can be fully controlled. The WebSocket can also be used in the same way. There is also UDP channel, which can be used for service purposes and allows the connection to the Iqrf IDE tool. The IDE is a PC program developed for configuration, testing, and diagnostic of the Iqrf network. For those who want to develop their own applications running on the Iqrf gateway, there is the MQ channel, which makes the Iqrf Daemon application interface locally available to the other processes. There are also several types of physical interface to which the Iqrf transceiver can be connected, namely SPI, UART, or USB. So the user can configure the one he wants to use. Finally, the Iqrf Gateway Daemon sets the running mode of the Iqrf gateway. The default state is called operational. In this state, the gateway sends requests to the Iqrf network and receives responses and forwards the data to the configured communication channel. In forwarding mode, the gateway also forwards the low-level communication protocol DPA to the Iqrf IDE terminal, allowing the lowest level communication to be analyzed. Finally, there is a service mode that can connect the Iqrf transceiver directly to Iqrf IDE tool, allowing to use all its functions. But there is much more if we go a little deeper. Important components of Iqrf Daemon include scheduler, uploader, and Iqmesh Services. The scheduler will allow you to set up periodic reads of the Iqrf network, so sensor data is regularly sent to the cloud through MQTT, as is common in most systems. The uploader will allow firmware upgrades of the Iqrf transceiver. This can be done directly in the gateway or over the air in case we are updating the firmware of any module in the network or the whole network at once. The component Iqmesh Services put at your disposal services necessary for the installation of an Iqrf network, in particular discovery and auto network. There is also network enumeration service that stores important system data in a database, or a backup and recovery service with which any device on the network can be replaced. The Iqrf Gateway Daemon is also responsible for communication with the Iqrf repository, which is a server that provides important information for various types of sensors present in the Iqrf network, such as firmware version, type of measured quantities, and so on. Last but not least, the Iqrf Gateway Daemon communicates with the web application, which provides a graphical user interface that allows the gateway to be easily configured. So, what is the Iqrf Gateway application interface? After you set up the communication channel, the gateway can be controlled using structured JSON objects. The application interface offers several categories for controlling the Iqrf network and for setting gateway parameters. To communicate with the network, the generic format can be used to communicate directly using the DPA protocol, which is a lightweight byte-oriented protocol used by the TR modules themselves. However, it assumes knowledge of the DPA protocol. It is also possible to use the Iqrf standard format, which is a kind of abstraction over DPA that simplifies communication for devices that have implemented the Iqrf standard sensor protocol. In addition, this protocol allows the use of drivers for sensor devices supplied by the Iqrf repository. This mechanism translates the sensor value from the DPA format directly into a readable format including SI units, which is the format expected by most cloud services. Another category offered by the application interface is Iqmesh Services. These services are responsible for creation of the Iqrf network, and they are required for the installation of an Iqrf network. The application interface can also be used to directly control the scheduler component. This allows setting up regular readings from the Iqmesh network. There are also additional services in the application interface for managing and configuring the Iqrf Gateway Daemon itself. Part of the open source project for the Iqrf Gateway is also its web interface, which provides access to Iqrf Daemon services and also offers some custom ones. The user has the possibility to find out information about the status of the Iqrf Daemon service, analyze the system log, access the secure shell, upgrade the gateway firmware, and also manually set the MQTT communication channel, WebSocket, or scheduler. The Iqrf network section has most of the tools for administration and management of Iqrf network. To support the gateway connection to some cloud services, the web interface includes a wizard to simplify the connection configuration. Iqrf Daemon was originally developed for Debian-based systems. However, as time went on, there was a need to provide more stability to the gateway, which is related to write error of the SD card that carries the operating system. The solution comes in the form of Yocto Linux, which is running in RAM of the Linux machine, and the SD card is used as read-only. The Yocto branch also comes with Mender support, system for mass management of Linux machines. However, the original Armbian solution is still maintained, mainly because of its easy extensibility with custom applications. As a next step, we are working on extending the communication possibilities with an Iqrf Bridge device. This is a simple and cheap device whose task is only to provide connectivity to the Iqrf network via Ethernet or Wi-Fi, and thus to replace the Iqrf gateway in some cases. More complex functionality remains concentrated in the Iqrf Daemon. The Iqrf Daemon can run on the Iqrf gateway or on another server completely independent of the location of the Iqrf bridge. This solution is particularly useful where multiple independent Iqrf networks are needed. The Iqrf Gateway Daemon and Iqrf Gateway Web Application projects are designed in a modular way. Both Daemon and Web App have their basic functionality already defined, ready as an open source. Further extensions are planned for both Daemon and Web App under software license. Licensing arrangements are being worked out. Licensed will be components for working with multiple connectors or bridges, also collections of data from Iqrf sensors, analysis, alarms, and possible transformation of data to different formats. A web-based license server is planned to provide licenses to individual users, customers, after payment of a fee via eShop. Licenses can be time-limited for testing or time unlimited. Daemon components and web app under license will not run without correct license. So, if we look at the overall scheme, we can see that the Iqrf gateway is a very versatile device that allows, on the one hand, complete management of Iqrf network, and on the other hand allows to connect this network to both local devices or remote and cloud servers to create a real IoT system. Let's focus on the hardware of a gateway now. How to connect Iqrf transceiver to any Linux computer? The design of the basic Iqrf shield is very simple. Basically, you only need to connect the SPI communication bus. To achieve better stability of the Linux machine, you also need to control the power supply of the TR module. To do this, the shield needs to be equipped with a simple circuit controlled from the Linux machine that controls the power supply of the transceiver. For the same purpose, it is also necessary to decouple the SPI bus, for example using gates, and enable the bus using a control signal only after the Linux machine is initialized and the Iqrf Daemon is operable. Both of these control signals are implemented within the Iqrf Daemon. For status signalizing, it is also recommended to connect two-color LED to both the Linux machine and the Iqrf transceiver. The connected button allows triggering some functions of the Iqrf Daemon, for example to turn off the gateway or reset it to factory state. The basic shield can be extended with some additional features that enhance the usability of the Iqrf gateway. In some of our designs, we use an additional processor that plays the role of an external hardware watchdog. The Linux machine generates a periodic signal that is detected by the MCU. If the MCU stops receiving the signal, it performs a reset of the Linux machine. In addition to the SPI bus, we also use the UART. This takes the role of the main communication bus, and the SPI is used to support low-level SPI programming. The newer shields are also equipped with a serial RAM, which is connected to the TR module. This is important for Iqrf networks that use so-called beaming sensors. The beaming device periodically transmits measured values. A shield equipped with serial RAM will allow the Iqrf gateway to receive and store these data and forward it immediately in case of higher priority. To simplify the secure bonding of the new devices to Iqrf network, we use an NFC interface that is fully controlled from the Iqrf transmitter. For proper communication, we need to ensure separate connection of communication buses of the Iqrf shield, all under the control of the Iqrf Daemon. Due to the need for use in industrial environments, there is a requirement for use in a wider temperature range. For such systems, it is better to abandon the cheaper Linux machines using SD cards and replace them with a machine with integrated eMMC flash, such as the Raspberry Pi Compute Module 4. Since this is a compute core, a custom motherboard with the peripherals needs to be designed for it, or existing commercial solution can be used. This design is fully based on the functionality presented in the previous slide, but we extended it with a backup RTC to enable timing for offline systems. Also, a sophisticated power management is used in this case. Extension in terms of communication physical layers are also important. The use of Compute Module 4 will allow for Wi-Fi to be added to the basic Ethernet communication. For industrial systems, the use of LTE connectivity is also crucial, as local area networks in factories will not usually allow third-party devices to connect. LTE also has a key role in street light systems, where other connectivity is not an option. Adding LTE connectivity is possible by connecting an LTE modem using the Compute Module 4 USB interface. The biggest challenge is to create an off-grid gateway, a gateway that operates independently of the presence of electrical power. This device is already quite complex compared to a simple shield. The biggest challenge we faced here is to ensure the lowest possible average power consumption. This project, which we are currently working on, is co-financed by the Ministry of Industry and Trade of the Czech Republic. The off-grid gateway is based on the original concept, but it's supplemented by several other subsystems. It is mainly an electricity generation and storage system, which includes a solar panel with maximum power point tracking regulation, charger for 2 LiFePO accumulators connected in series and supplemented by a load balancer. This system can recharge the battery even in a negative temperature. Also, the usable capacity of the accumulator is significantly reduced. Therefore, in this design, a great effort is put into the system to minimize power consumption. A strategy is chosen such that the gateway periodically switches between communication and sleep. In this way, the average power consumption can be reduced very effectively. It should also be said that while the gateway is sleeping, the Iqrf transceiver can be active and still receive and store data. The forwarding of the aggregated data will only occur when the rest of the hardware is activated. The activation period of the Iqrf gateway can be variable. The reducing of the consumption of the gateway is at the expense of the frequency of data transmitting. This is particularly useful during the winter month, where the accumulators cannot be recharged to 100% capacity. To minimize power consumption, the gateway hardware contains special circuitry that physically disconnects all the hardware from the power and reactivate it after a set period of time. From a software perspective, in addition to Iqrf Gateway Daemon and Iqrf Web Application, the gateway is complemented by two additional software modules. First module is dedicated to communication cycle timing, which performs a controlled shutdown of the Linux machine and subsequent setup of the circuitry responsible for voltage control, including timing and subsequent wake-up of the hardware. The second module is responsible for the native connection of the Iqrf gateway to the Iqrf cloud, which is also part of the whole project. In addition to Iqrf and LTE connectivity, this gateway is also equipped with the LoRa module. It serves as a backup communication channel. For example, in case of low battery capacity, the entire communication chain will not be activated. Only the status information will be sent using LoRa channel. The average power consumption of the current prototype of the off-grid gateway is approximately 21 mA for 10-minute communication cycle and about half of that for 20-minute cycle. The consumption when the gateway is running alone is 208 mA and when sleeping is 360 microamps. With this average consumption, the gateway can last 17 days online at accumulator capacity of 4.4 ampere-hour, which provides enough reserve to bridge period of no solar activity or freezing periods when the accumulator cannot be fully charged. We are currently testing the use of both 5 watts and 20 watts solar panels. The project also includes the Iqrf cloud, which becomes a natural part of the whole system. Its role is mainly to manage and configure the gateway and the subordinate Iqrf network, and to make the data available to third parties for visualization and analysis. Therefore, a gateway edge management layer is created at the gateway software level, which interacts with the cloud software. The cloud provides basic functions such as auto-provisioning, secure automatic connection, and then heartbeat monitoring of the running of the gateway, displaying its status, including the status of the charging system, battery capacity, etc. The Iqrf cloud also supports backup of the Iqrf gateway as well as the backup of Iqrf network, including parameter configuration. It also includes some of the most basic Iqrf network management features, such as auto network or discovery. Thank you for listening.